The thing to remember, you guys, is we spend the first day almost exclusively on R. The second day almost exclusively on specific R routines, and then we begin the transition onto the pipeline workflow environment. And today the goal for me would be, at the end of the day, to tie up these atomic processing tools. Remember the 20,000 R libraries with multiple functionalities and whatnot? I typically refer to them as individual modules. They do one thing really well and one thing only. They are not necessarily designed to work well with all kinds of other things. The reason is that if you know how one little component is supposed to work with something else, of course you provide that API, that application programming interface. You make them interoperable, no problem. The issue arises that many times we just don't know who's going to be the client, who's going to be the consumer of that functionality, not human, but machine consumer of that functionality. And that's where exactly the issue arises with complex computational protocols. So again, the important point for today for me would be to have you work on a project at the end where we draft an R script that we're going to wrap as a pipeline module and embed into the middle of some kind of a workflow protocol that does something interesting, okay? And this is going to be obviously an example, and if you have other R functionalities or other MATLAB, so there is some MATLAB coders here, right? I can show you how to do the same thing with MATLAB as well, but this would require you to build a specific MATLAB bindings that are specific to the server that the code is going to run on. It's not like R scripts. R scripts are interpreted. You don't need a compiler for an R script. You need to have the R environment, obviously, and the package is built for your system. But at invocation time, the same script works on every single platform, exactly the same. And that's why, remember when I showed you the table that compares R with IDA, MATLAB, Scala, Spark, the other things, C, Java. The trade-off of this efficiency and portability of R is performance. Right? It was the bottom performer in terms of computing. But there's ways to optimize it. In the ebook, there's plenty of examples. If anybody's interested in, why should R be at the bottom, there's ways to very substantially increase the performance. Okay, so we started with the pipeline. I showed you the workflow miner, and then I kind of generated one workflow that I loaded, but it was schematic. Remember, it didn't have much. It just had a few modules connected, a couple of disconnected pathways. It kind of gives you a skeleton of what might play a role in the analysis that you specified as a keyword or a key phrase to pull out of the knowledge base of the pipeline. This is a huge research problem, you guys. How to find the appropriate tools that are going to talk to each other and can be streamlined into an end-to-end solution. It's a huge research problem, unsolved. So the miner addresses this, but it's not a perfect solution. Then I showed you the library, and then I showed you the workflow documentation. So let's go ahead and, at this point, remember, we actually defined one module from scratch, remember? It was a silly module. I think I used cat or more or something, essentially to pipe in a file, push a file to the server, and read the content of the file back to us, kind of a silly thing. And then we drafted one workflow from scratch where I registered a few things. What failed for me at the end was when I wanted to visualize the results of the pre-registration and the post-registration volumes. It complained that the Java something was not opening, and it's a Mac specific issue. I don't know exactly what the issue is, but So we have an example of defining a module, and these module definitions can get very complex, okay? But you got to do a little bit of the reading of the documentation of the pipeline environment if you want to do something very elaborate. Oh, and I did promise to fix that link. I'm sorry, I will fix it. I did promise to fix that link. It's a little thing here. So if you want to know more about it, again, on the pipeline.loni.usc.edu, the quick start guide and the user guide kind of provide additional information about how to do more complex module definitions and more complex workflow definitions. Just to give you some examples, a module is not necessarily something that sits on the distributed pipeline server. It could be a local executable, it could be a web service. Think about a database that kind of listens to queries and returns back a table or some kind of metadata, or maybe even the data itself through HTTPH protocol or some kind of other protocol. The workflow definitions can get very complex as well. For instance, if you want to connect two modules, but the results of the first one don't directly feed into the inputs of the second one, okay? Oftentimes people write code that kind of assumes the names of the outputs perhaps from the names of the inputs, or they generate unknown types of outputs. There's plenty of examples like this, okay? Free surfer is one of those examples and whatnot. In this case, you literally don't know what the input is. So the pipeline provides something that's called flow control. That's a dashed line that kind of waits for the previous module to finish and then starts, okay? And then the wrapper of the secondary module, the receiving module, needs to have an appropriate understanding of the implicitness of the unknown characteristics of the outputs of the previous module, so that it can look in the proper place, find the proper names, and then ingest that result from the previous module internally to do the subsequent processing, right? Is everybody kind of with me here? So there's lots of complexities. I'm just, you know, trying to convey that many of these can be handled gracefully. But of course, there is certainly examples, and I know of examples where you can write a script that cannot be fully or easily implemented as a pipeline workflow, simply because the script may be doing some I don't know, regular expression operations. You know, there's lots of things that you can do with scripts that have 50 years of development in a scientific community, and you know, the elaboration of the syntax for scripts is just, you know, overpowering. Nothing like this is available in the pipeline workflow language, this XML language. But of course, the most common things are already implemented. So I showed you the navigation of the library. Let me open another tab here with the corresponding wiki docs. Okay, it's loading slowly. And then what we're going to start off with is just going over the logic of some of these common neuroimaging workflows, okay? Some of them we can run, some of them we can, you know, do at a later phase. Okay, so here, so remember, I guess for us, these are going to be the important ones. There's additional ones below, but let's just click on the standard ones. And so there is one functional pet module that we recently did. There is an example of what's called bagged objects. So sometimes the data comes in as zip archives of metadata and data into the same object. So these are called packet objects. There is also these ARC and digital object identifiers that can be assigned to data objects, so that if you have a data set that has an interesting characteristic and you want it citable by itself, not the manuscript that reports on the data or the findings about the data, but the data itself, you can create a, everybody's familiar with DOIs, right? Digital object identifiers. So these are essentially unique, uniform reference labels that every publication, every scientific publication in a peer-reviewed journal would have a unique DOI identifier, so that going to the DOI.org domain and providing the DOI is going to send you directly to the manuscript itself. Now, some of these manuscripts you may or may not have access to because of copyright issues, but the abstracts are always available, so you can kind of at least see what the focus of the specific publication is. And for at least, I'm not exactly sure how it works in the rest of the world, but in the US, most of the research that's funded by the federal government is required to have all the scientific manuscripts published and open access within 12 months of publication. So even if you go to a journal that is proprietary and they have a purchasing or a licensing or something like this required for you to view the manuscript, 12 months after publication, the paper will be openly accessible without any special access. Again, this is for the US. I don't know exactly how it works at the home institutions that you are at. So these digital object identifiers can be assigned to data sets, which is very interesting. In fact, the University of Michigan has something called ISR, the Institute for Social Research, which is the largest social research institute in the world, and they support close to 20 or 30,000 data sets, each of which is very nicely curated, longitudinal, decades at a time. They're not just US, they're worldwide, because the ISR, the Institute for Social Research, acts as an umbrella of about 700 worldwide institutions, and I'm fairly confident that one of the Malaysian institutions, for example, will be a participant, and they would have their data into the ISR, ICPSR database, and therefore catalog, labeled uniquely, and so forth. So let me, before I start with some of these examples, I want to see the status of some of these workflows that we ran last time. So remember, we downloaded this, and I can, let me just show you what this thing looks like. The JNOP file is simply a set of XML, these are very similar to the pipe files, a set of XML labels that kind of say, what Java libraries need to be downloaded locally and where they need to be downloaded from. So this is just an instruction set of how to start a Java app, nothing else. That's why it's so light. It's how many bytes? This is 2 kilobytes. Very, very small instruction set, but when you start it, all of these jar files that I showed you a second ago, all of these jar files, the computer now is going to go to the corresponding URL domains, pull the jar file, and remember there were a whole bunch of places. So that's what it's doing right now. So it's starting, it's loading some of these libraries, it's checking with the server, and now what I want to do is I want to connect to my TryItNow guest account. So we see handshaking, authenticating, authentication done, so I have one connection now. Okay. So, okay, 4 sessions. Whew. I thought one of you might have wiped out my sessions, because remember I shared my guest ID, and you can actually go ahead and reset some of this. But I have four sessions. So let's see. This first one. So again, one of the beauty of that environment is this decentralization of the computing, the design, and the research investigator. These three things could be completely independently done at different locations, at different times, and so forth. So, you know, command minus and command plus, or control minus control plus, kind of gives you a way to zoom in and zoom out of this big workflow. And if you guys remember, so this is a group module right up here. If you click on it, it kind of leads you into the second level details. And here, again, the 4 panels. And by the way, oftentimes more experienced users, and users certainly that will acquire a full-fledged LONI Cranium Pipeline account. So to use the pipeline not as a guest, but as a full-fledged user, you have access to a shell script, and this info panel tells you exactly what is being run on the script, and it tells you something about the job and the session for troubleshooting. Okay, so and then the output stream includes what the specific code, in this case, this little script, MRI segmentation stats generated. So some of these as an output stream just printed in the shell. Well, this shell information is pulled and saved into that output stream. In the error stream, typically errors are reported here, and you can see these guys have a specific location in a session-specific location on the temporary space. And then you can essentially look at these things, download them, and view them. So so this file is right up here, and again I can go ahead and open this with a text editor. Remember, as we did before, and actually look at some of these results, parse them, send them forward. In fact, we have written certain scripts that aggregate these things across subjects and tabulate them into a nice layout, so that you can have essentially a table that has the cases as rows and the columns as some of these features that get automatically computed. All right, so okay. So this specific workflow, and by the way, there is, remember how I told you that for each of these workflows, there is typically a wiki page that's listed over here, and it basically tells you what it does. This workflow takes unscoped script raw MRI volume and generates tables of the total volume, total gray matter volume, white matter volume, and cerebrospinal fluid. So that's what gets outputted for this specific workflow. The next one was the brain suite that I believe had failed somewhere in the middle. Oh, this worked as well. This is another way to generate partial volumes, in other words, volumes for the 3 different tissue types. And the ones that ran a little bit longer last time, okay, there we go. So this workflow ran for 1 day, 1 day and 1 hour, I guess. It completed successfully. And now what I can do is, let me see, okay. First of all, that's a group module. I gotta go all the way down to the end. And at the last module, I can go directly to the output, select it, and I can either view it or download it locally. Let me just grab it locally because it may be more interesting to look at it, not as text, but as a spreadsheet. Okay, right up here, so let me see. Okay, so let me see if I can open that with okay, it doesn't work this way. Okay, this may not work too well, let me just see. If it doesn't work too well, oh, that works, I suppose. Okay. So look what's happening, you guys. You have these measures now. They're not necessarily labeled, but these are the 10 cases, 1 through 10, and then you have 1, 2, 3, a whole bunch of, let me see exactly how many. There should be 56 or so regions of interest. These are the corresponding volumes. So you see what came out effectively is, and why 10? Well, because up here, remember, I had as input 10 cases, right? Is that what I see? So if you were to put in here 100 subjects, you're going to have 100 rows in the Excel spreadsheet that I just showed you. And now the question would be, well, what are these 56 derived neuroimaging biomarkers? So let me show you. This is something very important that I'll show you with the logic of this workflow. Actually, let me see if I can pull out the metadata from here. Okay, so let me see if I can find this little quick column. So I'm going to search for the corresponding ROI labels just to show you what they look like. Okay, that may be. Okay, here's the ROI nomenclature. So here are your, the background is typically excluded because remember the background has nothing to do with the data. It depends upon the field of view of your scanner. It's typically irrelevant, so we're going to ignore that. But the 56 regions are listed right up here. And in fact, what you can do is copy these guys, go back to our Excel spreadsheet, open a new tab, plug them in, and then copy them again to do something more interesting, namely paste it by transposing transpose, okay? And now, you guys, I can copy these guys, go back to my front page, include, okay, insert the copy, wait, and shift cells down, okay? But now the problem is that I need to shift them one that way. That's right, so let's copy these guys again and start it over here. All right, so does everybody see what I did here? I simply manipulated a little bit to put in the actual string labels for the regions of interest, so that if I'm looking at this number up here, this is subject 1, 2, 3, 4, 5, 6, subject 6, and the region of interest is the right lateral orbitofrontal gyrus. Is that right here with me? So imagine now the situation where you have, for each of these 10 subjects, the clinical data is the first columns, the genotypes, if you have any genotypes, is the next few columns, and then cognitive assessments, the next bunch of columns, and now we have derived neuroimaging biomarkers as the last columns. You're essentially ready to do some interesting analytics, just like the ones we did with the Parkinson's and ALS through R, right? Is that right here with me? So this workflow, again, takes a bit of time to compute, but it's certainly very useful. And again, it's called automated ROI extraction. All right, so let's go ahead and go over what's the basic idea here. So you have your cases, and then what you want to do is you want to choose. Well, first of all, before you begin anything, you have to select an atlas or a target, because remember, things need to be homologous before you start either computing or interpreting derived neuroimaging biomarkers. So this notion here of this brain scan, which is referred to as the reference volume, is a volume that represents the space that we want to embed every one of the individuals before we proceed with anything else. And then we also use the ICBM, the International Consortium for Brain Mapping. ICBM in our domain has nothing to do with ballistic missiles, okay? This is simply the International Consortium for Brain Mapping. So this is an atlas that's going to be used in the corresponding skull stripping. I'll show you in a second. And then you have your actually input data sets. So by the way, I mean, everybody probably should be opening that workflow. It appears right up here. It's under LONI, automated ROI extraction, the second one. Okay, if you guys want to download this. Okay, and then we go into the first group module, which is called volume pre-processing. That's where you do some of the work before the analytics actually start. Let's go ahead and open this and walk you through what it does. So, well, why don't you tell me, what should a pre-processing of a structural brain scan study include? What should a pre-processing include?
Artifact removal.
Removal of what?
Artifacts.
Artifact removal.
Then orientation.
Skull removal. Do you say reorientation? Okay, reorientation, if anybody does not know what this means, is if the data, remember how I told you the indices, X, Y, and Z indices, depending upon how they're swapped, it kind of tells you if the volume is sitting in a standard axial space, or sagittal space, or a coronal space. And if one of your subject is sitting like this, and the other one is sitting up, and you start doing this, the registration is not going to be able to deal with this kind of situation. It's going to try to fit it like kind of the opposite way. So, reorientation, what else?
Size.
Right. Spatial normalization, scaling, right? And you know, morphing. And we'll talk a little bit about that soon. What else? Well, okay, so parcellation, okay. What else? How about, are you familiar with drifts of intensities that need to be corrected via not the inhomogeneity software. So in other words, when the brain scan is acquired, there would be typically, because of a variety of reasons, okay? There may be, the image may appear brighter or darker in some part of the field of view, okay? This has to do with the magnetic field not being completely homogeneous. Variety of things, feelings, tooth feelings, and all kinds of things play a role for this drift. And of course, the MRI technologies that set up, they do a shin scan and they try to correct the gradients and they try to minimize some of these technical aspects before the scan is acquired, but typically there is still a little bit of drift. And remember, if the same gray matter tissue in one region is a little bit higher than in another region, then you as a human would be able to see it, but for the machine that doesn't have the notion of a shape that's intrinsic, they look like different intensities. So the potential for misclassifying voxels is huge. So intensity and homogeneity correction is another. So in this case, what's happening is, here is your reorientation that we said, you kind of place the volumes if you have to. And by the way, this reorient, in addition to that, does a scaling of the intensities just to make sure that everybody's on the same range, so that there is no too heterogeneous things. Here's your bias field correction to correct inhomogeneities of the magnetic field. And now here is this skull stripping meta-algorithm, which is a very interesting thing that we wrote back in 2008. One of our graduate students actually wrote. So what it does is it looks at 5 different skull stripping methods. And skull stripping, believe it or not, is a very difficult task. Why? Well, because it's just difficult. There is, the tissue is connected, obviously. The brain is not surrounded by an empty space or by a space that's homogeneous, water or a duro or something like this. There is all kinds of complexities where you either cut too much into the brain when you auto-segment, when you auto-skull strip, or you leave some non-brain tissue on the surface. Very commonly, it's very difficult to know. And you can't correct this topologically because it's the same topology. You can't correct this via intensities because it's the same intensity. There is no gradient here. So it's very, very tricky to do these kinds of things. So what this student did, back in 2008, and he says, we're going to be looking at 5 completely separate and independent skull strippers. We're going to bind them together, and we're going to use voting to have them, the wisdom of the crowds, direct whether a voxel is included or not included as part of the brain. So it is a very expensive algorithm. There is many other ones that work in, a minute, even less than a minute. This one takes 22 minutes. Very expensive algorithm. So we skull strip, and then the first thing that we do is co-register. FLIRT is a linear registration method of the FSL package. And you see right up here, you specify, it's got many parameters. Let me just show you. Copy, new, paste. So it's got many, many optional parameters that we haven't included here. Input weights, 2D, a whole bunch of things here. You can specify the cost function, interpolation, right? Because registration actually has 2 steps. And last time I actually showed you the 2 steps completely independently. The first one is you look at the 2 things, the 2 brains, then you derive a displacement vector field that says every voxel from the input volume needs to be placed in that direction that far to match the target brain or the atlas brain corresponding homologous voxel. So you essentially first compute a displacement vector field, right? And now you need to reslice the input volume according to that displacement vector field. And that's the second step. And in the AIR package, in the automated image registration package, these two are coded completely separately as two different modules. Remember right up here. This one. No. Oh, this one, right here. Okay, I might have killed that session. Anyways, so here in the flirt package again, you can actually specify the interpolation, and it's various things can be included there. In our case, we simply specify that we're going to be using a 12-parameter registration, which essentially means full parameter affine three-dimensional morphing. Affine means that points in space are kind of the distances between points in space of the original volume are going to kind of be semi-preserved in the output once the volume is resliced. It's a little bit more rigid than the non-linear registration. The second parameter says the type of the data. Remember, I told you there is all kinds of types here: short, byte, integer, float, double. So character is 1 byte, short is 2 bytes, integer, float are 4 bytes, and double is 8 bytes per voxel intensity. So you can specify what that is. And then you have the reference, which is the target of the registration, and the source or the input, which is the data that you want to reslice. So that's what happens up here. And now once you've done the affine registration, the two brains of the atlas and your data are going to be roughly speaking in the same dimension, roughly speaking in the same space. However, there could be small local variations that the linear transformation cannot capture because it's global linear, right? Everybody's familiar with a line, right? It goes as a straight line. But if you want to stretch and compress and stretch some more, you need a higher order cubic, for example, registration or something. So right up here is where we do the B-spline deformation, which comes from a totally different package, which does a little bit more to the registration. And once you have the data non-linearly morphed into the same space, you go into the parcellation. Okay, here is where you divide the volume into 28 and 28, mostly gray matter regions, right? And this is done using, again, machine learning methods. And once you come out of it, remember, so what you've done is, you guys, diagrammatically speaking, you start with a raw data set. You do all kinds of manipulations to it. Next, what you do is you linearly scale it in the atlas space. You non-linearly scale it to make the fit better. Then you parcellate it. And now you got to invert some of these operations because you typically want the labels to be in the native space, right? Because if your original data is in this space and your parcellated data is in that space, you can't overlay it, right? So that's where the ITK inverse transformation puts the data back into the native space. And then you're going to do the affine inverse of the linear transformation that you did first. And remember, the order is very important. Why don't we do non-linear registration first and then linear? Would anybody care to guess why the linear registration always must come first? These operations are not commutative, right? Very, very highly non-commutative operations. The reason why you don't do the heavy-duty non-linear registration first is that it's very intrusive, and it's essentially going to be fitting very localized details to an image that can be very, very far from the target. So applying the affine, and people sometimes do just rigid body, just literally take the image and move it like this, 6 parameters, without any scale or shear. You just move it 6 parameters to put it in the same space, and then you go further, okay? But you got to do the affine so that you preserve the global orientation and the global characteristics first before you try to do a localized regional match of the corresponding tissue, okay? So the order is very important, and exactly the order in which you apply, the reverse order needs to be applied at the end. And now here is another reorientation at the end, just to convert the type to byte. And then once you come out of here, now first of all, you save those labels, because again, and now look at this trick here. You essentially put them in a temp space with your guest user ID, and then you make a directory called brain parser where these things are going to be stored on the server. Okay? And then you go ahead and compute. Now that you have parcellated the data, you have these 56 plus background regions. You are essentially converting them a little bit and using FreeServer to compute the volumes of all of those. And now once you're done with that, remember, this is done one case at a time. So the FreeServer, where was this? The FreeServer generated data that looks just like these. Remember, you guys? So very, lots of information. And then what you're interested in is you're interested in these numbers only. So we wrote a script that pulls all of these numbers and aggregates them across subjects and nicely tabulates them so that we can generate this final result. That's what's happening up here. And this is, I mean, to be honest with you, I'm not a huge fan of this, but it kind of works. Okay, so there is a sequence of, remember how I told you that some things are tricky? Because remember, you have to open every one of these files, find the location of where the value of interest is located, pull it out, continue, find the next location. So it's a very complex operation if you think about doing it by hand, even for a human. You got to train somebody how to do it. A monkey can't do that. A kindergartner is not going to be able to do it. You got to train somebody with some expertise to pull these things out. So that's why you have a sequence of grab, squeeze, balance, draw, cut, paste, transpose. A lot of scripting wrappers to get this from the messy output all the way up to what I showed you was this. What was my Excel? Yeah.
So for this particular kind of segment, would this make more sense to actually have a script that you created that's performing these transformations in R on a data file?
Yeah, absolutely, right. This can be done many different. See, this is not an issue with computing. This is an issue with data wrangling, and because all of these software tools, they come from various groups. Everybody likes their own syntax for the outputs, so it's very difficult. But yes, the manipulation, the extraction of the specific data elements you want can be done in any language, and can be done much more elegantly than what I'm showing you here. This is just one example. And by the way, these are simple Linux commands: paste, grab, regular expressions, kind of. Very technical, but very foundational commands, as opposed to a higher level language that can do it quicker and maybe even more efficient. Anyways, so and then you save this table out in the results text file. Okay. So are there any questions about this process? Again, it goes. This is your end-to-end. You wanted an end-to-end example last time. Raw data sets, tables at the end, right?
What is a good way to kind of like, because it's kind of like complicated, those somebody has to use. What is the best way to kind of like, just to get an overview of like, let's sequence of things, like one of the things that you did is that you point at the output node, and there's this thumbnail
Right, so, right. In the web app, which I haven't shown you yet, in the web app, which is kind of pre-production release on the website, right up here, we've coded another alternative way of looking at, see, this is process or function-centric display of the protocol. Does everybody agree with me? The data goes from step 1, step 2, function 1, function 2, very process-oriented. In the web app, we've actually coded a very nice view where you can actually see it's a data-centric view of the process, and it doesn't show you the modules, it shows you the type of stuff that gets generated at every point. So you get essentially, you get a graph where the nodes are thumbnails of either image snapshots or tables or something that kind of illustrates the flow. But again, it does not necessarily resolve the complexities that come up with an algorithm like this. It's intrinsically complex. And you know, for this specific one, for instance, let me see where it's located. Automated. Let me see. Okay, it's probably this one. Right, so you see, you need to go to the description, and the description kind of tells you a little bit about the inputs, the pre-processing, you know, the parsing. It kind of gives you a textual, almost verbal description of what the protocol does. And then it has a snapshot of the workflow, a download of the actual pipeline, and some footnotes or examples and whatnot. And kind of, you know, there's publications with it. It shows you the type of tools it's using. So the documentation actually might be helpful with some of these workflows. All right. So, okay, so that's that. So let me go back then and see what was next on our list here. Okay, the global shape analysis. Yeah, this is a good one to have a. Yeah, so let's go ahead and try this one. Now what I did is okay, so let's go ahead and first of all open this. Here's the global shape analysis workflow. So this one goes a step further, you guys. Is what it does is, in addition to what we saw earlier, parcellating and computing simply the volumes of every one of these 56 regions, it's going to add another very novel feature of computing morphometry shape measures on each of these 56 ROIs. So imagine the volume as a measure of an object is very unidimensional, right? Because I can show you infinitely many objects with the same volume, but vastly different topology. Does everybody agree with me? And vastly different geometry. Think about a balloon, right? You get a balloon, you poke it, you squeeze it, you pull it. You know, it's the same area inside, it's the same volume. But its shape, its morphology will be vastly different. So that's why you have to go sometimes to higher order metrics to be able to detect you know, motifs or traits that are detectable using the imaging. Okay, you know, so in this global shape analysis workflow, which by the way is available over here under, and it's got different types right up here. Global shape analysis, 3 groups, 2 groups, post shape representation. They're kind of split into different things. So it resembles this one in the beginning, as I showed you, but it's also somewhat different. And I want to walk you through this because it has a nice twists, and we'll see how we can maybe plug in a new data set and run the same workflow with. So, let's go ahead and stretch this a little bit. Zoom out. So, it also comes with, I don't know, 10 cases. 10 cases just to show you what it goes in. But it has something very interesting, guys. In addition to the actual imaging data, do I see it? In addition to the imaging data, it has the metadata inside of it. So right up here, there is metadata as stored as XML files. I just double-clicked on one of these XML files to see what kind of metadata is available for each of these individuals. And you can see here we have, these were Alzheimer's disease individuals, so level of education is very important in dementia. Why? Because it acts as a buffer, apparently. You can have two individuals that have exactly the same brain atrophy in terms of their imaging scans. The ones that tend to be highly educated tend to be cognitively slightly better, and the hypothesis is that the cognitive reserve allows you different connections to, to support the loss of tissue, and you may be able to get from point A to point B where somebody else may not be able to, simply because you might have formed parallel pathways or something. Anyway, so level of education is important, the gender, the age at the two different time points when the subject was measured, and then an indicator of whether they're a patient, an MCI, or a control, mildly impaired, severely Alzheimer's impaired, or control. And then a unique identifier, and then here is your reference to the actual imaging data. Right? Simple, right? I'll show you a more interesting example in a second. But now, the idea now is that what we want to do is we want to break these 10 individuals into the 3 different groups, process the 3 groups separately, and then look for between group differences. Is that right here with me? Okay? So, okay. So group 1. Look here. Look down here, you guys. Group 1 has a. We have tried to de-identify the data here because this is, supposed to be synthetic data. Okay. So groups are going to be called Group 1, Group 2, and Group 3, for again the reason of having. We can't release human subject data. So there are just 3 different groups now. This metadata is included in these XML files, and the representation right now is not, they could have been labeled, they could have been AD, NC, MCI, whatever. It doesn't, they don't have to be numeric, is what I'm saying. They're categorical factor labels. And each of these groups has a grouping criteria, which is based on the group variable. And then, look what happens next. Next, we're going to split the 2 groups into Group 1. Let's look at this specific. So Group 1 has the condition. You see, stated as a subject belongs to group, and then it says Group 1. The next. So by the way, these are called conditional modules. They correspond to if-else statements in any language or script language. Okay? So these are branching in the workflow, and then you obviously can merge components from different branches. So here is an example where the condition is the subject belongs to Group 2. Okay? And then what we do afterwards is we do the between group statistical analysis, which includes these scripts to create lists, reslice the groups, transpose table groups, and do statistical tests. In this case, parametric t-test on some of these groups. And then what comes afterwards is you compute the group 2 versus group 1 p-values. And then you pass those on to specific ROIs, and you essentially make a scene. So what results at the end of these, and if you want, we can probably start this workflow and I can show you what it looks at the end, because it does take a little bit of time. It does take a little bit of time, but I'm going to start it. And probably by the afternoon this would have finished, so we can actually look at these results. They're very interesting to see. So it's retrieving the workflow from the server right now. Okay, so I'm gonna, let me think about that. Do you want to start this with the default data, or do I want to show you how you can embed your own data? So let's take, before I run it, let's take one step back here. Right up here, I provided you guys with something that's called design matrix. Let's go ahead and save that CSV file locally. No, this should be called, let me just get the right name. This should be called, okay, that's how you do it. You grab it with the mouse, get the name, and then save as, linked file as, right, and we're going to give it the very same name. Right. You guys, I just downloaded this file. Let me show you what it looks like. So this, by the way, is called a design matrix file. It's a very simple file format that stores some kind of an identifier, column labels. And then the second column always has to be a pointer to a specific imaging file. So for example, this does everybody see? It's a very, very long name. Well, it is what it is. We're not going to deal with this. It's a very long name to a nifty file. Okay? And here's your subject identifier, completely irrelevant, but in there for the purpose of maybe you want to know who that person is, because the imaging file was so cryptic you may not know, especially when you have a whole lot of things. Research identifying number, yet another index. You can have multiple indices. And then comes the label of the clinical biomarkers, diagnosis, age and gender, weight in kilogram, handedness, are the individual right-hander, left-hander, MD, whatever. And then marital status, education level, ApoE label for genetics, ApoE allele 2, and the first one was allele 1, allele 2, and Apo itself. Then you have mini-mental state exam score, a cognitive measure of cognition, clinical dementia scale rating, CDR, and then a whole bunch of other things, limb total and LDL total, EDAS-COG, some kind of a cognitive score, I forget what it stands for, GDS, dementia scale. Does anybody know what these things stand for?
Genetic dementia
Right. So you see a whole bunch of things, right? A whole bunch of things that you have. And now in this case, we have, oops, trying to minimize. In this case, we have 33 subjects. And the important variable, of course, here is the diagnosis of 3 different groups. So what I'm going to do, so that's called the design matrix. Again, it's a design matrix because it has almost the complete information about these subjects, including references to their imaging. And you can have multiple imaging files, as well as metadata. So let me close that. Don't save. This we probably don't need anymore. And now the trick I want to do is I want to see if I can drag and drop this Excel file directly into my pipeline graphical canvas. And it says, okay, module name. Okay, let's remove that underscore. Remote server, the path, the data path column is the second column in my case. So I think I click OK. And now you guys see, I have exactly the same, it's called study module. Okay? I have exactly the same study module as was provided by the default workflow. So now I want to swap that. I want to pretend this is your own data. Now remember, this data actually came from here. From here, your data is going to come in from wherever. Now, you have to be careful because the references to the imaging data in the second column that I had to be properly set. If they're not there, it's not going to be guesstimating where your data might be. So you got to be careful with this. But with this example, I can now begin, and if you're modifying a workflow, never just remove the whole module because you're never going to know where did the afferent connections go to. You always remove one connection at a time and hook it up precisely where it needs to go. All right, guys, do you want to press on? Sorry for the little distraction here. This is a little sensitive here, but I think I worked it out. So remember, so this is the module I just generated. I'm trying to remove the default module that came with the data, this study module. So I want to plug in the data that we have from our Neuro Excel that we just downloaded. In general, this is going to be your own file. So I'm just drag and dropping it here. It wants a name for it. I'm going to give it a name. Specify that the data is in the second column. Okay, that. So here is this new object now that we have. And what I want to do with it is I want to open it. And you see there's nothing in it, so I'm going to say import data from this XML, browse to the local location, specify it, and then I'm going to say derive the metadata from the CSV itself. The second column is the important one that includes the imaging references, show the items. So what it did now is it found out exactly where are these images located, and mind you, they're located on the server, but for every one of them, it's going to generate here on this laptop an XML, right, these long XML metadata files. And if I go under grouping now, so remember I have 33 subjects, they represent 3 groups. I can make 2 groups if I divide them into handedness, or I can make two or 5 groups if I want to divide them by education level, you know, various criteria you can include. So I'm going to say, let's go ahead and generate groups that are based on diagnosis. So it says what kind of variable you want to, okay, wait. Before I do that, let me look at one of these guys. So remember, these are the local XML metadata that were extracted from the CSV and they were locally saved for us. So I'm going to open a random one, select the variable that I want to use as my grouping variable, let's say diagnosis, create a path, and I'm going to call this variable diagnosis, save it, and now here, if I generate groups based on this variable, yeah.
Did you use the Excel file or the one on the
No, I downloaded the, it's a CSV, it's not an Excel file, it's a CSV file, Excel loaded. I just dragged it locally, saved it locally, and I dragged it onto the canvas to get this study module started.
So what did you fix? Like earlier-
Oh, I didn't fix anything. I didn't have to manipulate the file in any way. I was just incorrectly selecting the groups here, and I couldn't get the metadata pulled out the right way. But I'm showing you how you can pull out the metadata the right way now. Okay, let's go ahead and start this over again. Let me remove these two guys. This is the workflow as it came directly out of the library here, right? Okay, I don't have any data. So what I can do, and in fact I can even, so copy, paste this one. So I just need a holder, a placeholder. And if you open this thing, I'm going to select all of them, wipe them out, clear all. Okay, and then I'm going to say from the local machine, import data. This is exactly the file that I downloaded from our website, right? Now, but you're not going to be. You have your own file, right? And then choose that file. And now here is where I did this thing wrong. So you have to say, before you do show items, specify that this is the second column that includes the imaging data, show items. And now this is going to tell me that I have my 33 subjects, okay, that were the, remember, these were the, here are the 33 subjects, right up here in this column, right? Okay. And then, now what I need to do is I need to create, okay, remember these groups, I need to wipe them out because they were the two groups that came up with the template of the workflow. I need to wipe these two groups. They have nothing to do with my study. And I'm going to generate new groups now based upon the new, oh, I didn't define a variable yet. Okay, so let's go back to here. Pull any one of these. Metadata XML to be generated for us from the Excel spreadsheet. And select the variable of interest, later I'll show you how we can do this with different ones. Add an X path for this variable. That's covered. Oh wait, do I put the brackets here now? Diagnosis. And then, which represents this variable. So I'm going to close that. And now I need to create new groups automatically from this variable. And now you see it goes ahead and says group 1 has 11 cases, group 2 has 11 cases, and the last one has also 11 cases. And it tells you exactly which subjects belong to this group based upon their diagnostic criteria, right? Okay? So now I can minimize these groups. 11 cases, it's a balanced design. Okay, that. And now I can remember before, in fact, I like to move these guys in here before I disconnect a line from the previous one. This one leads over here. And once you connect it, you remove it. And this one leads all the way down, here. Let's see if I can, okay, there we go. By the way, the neighbors are, oh, actually. Anyways, gotta go over here. Let's make sure we get this right. Okay, and now I'm ready to wipe out the previous study module because I've covered all the links that I had to. Delete that. All right, so is everybody here with me? So this is this is our old data now. Now, what I want to do is I probably want to, I don't know, give this thing some kind of a name, or maybe go to the workflow properties and say something about this workflow, right? Okay, so this is new workflow. Okay. And then I want to make sure this workflow is valid. So I'm going to do FOV for validate. It starts the validation process. And if everything is green at the end, this means that I've got a fairly good chance that if I were to run this workflow, it would generate appropriate results. Not necessarily, but a good chance. Almost done. So remember, now what's happening during that process is all the metadata gets sent to the server, the files are identified, they should be available, and it goes consecutively over all the modules, make sure the proper executables are available, they take the input that I provided, and by the way, look at this little connection that I drew up here, you guys, because it expected a file of this type, and I provided an NII image. It on the fly used the smart line to transform the data in appropriate. Okay. It says the files do not exist. Strange. Okay, hold on. Let me see if I can find out why are these files not there. Everything is okay, but it cannot find the files. So what I'm going to do is I'm going to try to find the files manually. If it lets me look for them. So let's see, that's the long file name. File is there. Right? Does everybody see the file? So the file is there. So there must be something in the Oh, I beg your pardon. So I think I need to switch that to cranium. Let me see if that's going to work. Let's try to validate again. See, this specific, I had indicated that the data lives on the local machine on this specific Mac, And maybe that was the problem. So hold on, let's see if that will validate. Okay, that's okay. So it cannot find the local files, but I can skip that, ignore these warnings. And let's see if we can run this. It wants to give it a name, yeah, let's keep that name. And I'm gonna start this. So if it starts running, I reckon this may take, yeah, it's gonna take some time, but I really wanna show you guys what comes out of the end, something very beautiful. You're gonna have these three-dimensional scene files that represent the stereotactic space of the regions that are different between the three groups. So, in other words, right up here at the end, this module, let's make sure this is running properly. Oh, but I wonder if I modified the groups, so hold on one second. Let's see what happens here. Okay, so look what's going to fail here, you guys. I did not give the proper group names once I swapped the original module with my own data. And my group names now are called diagnosis equals to 1 and diagnosis equals to 2, whereas right up here, the group 1 and group 2, look at the evaluation logs, it expected to see group 1, not diag 1 or anything like this. So I need to go ahead and change a little bit the group names to group 1, group 2, and group 3. So unfortunately I have to stop that to correct that mistake. So I'm going to reset. Yes. Let's go back to here. Go to the grouping and now give this group a new name. Edit group name. Let's just call it group 1. Okay. The next one is going to be group 2. Space in between. And the last one is obviously going to be group 3. So that I have something that's consistent with the subsequent. Or I could have modified the conditional modules as well, these if-else statements. Okay. So now the groups are called group 1, group 2, and group 3. And let's just double check that condition here. Okay, group 1 is the condition here, that's good. And this condition should be group 2. Okay, so I think that would be better. So let's go ahead and save that. FOS. I'm going to call this GSA. Okay, so I'm calling this global shape analysis. The number of subject is 33. So let's run that. And if this starts running, okay, and we see that the bifurcation does split them into 10, 10, 10, we're going to let this run for a few hours. And by the way, some of that information is available right under the user guide under study module. Right up here, study module. You guys can read a little bit about both conditionals and metadata. Oh, and by the way, this is something that I'm not going to show you, but oftentimes what you want is the workflow that we just ran a second ago that generated the 56 volumes for every subject, remember? The design matrix that we started off with, remember, only had the demographics and the clinical scores. Metadata augmentation refers to after you compute the image in derived measures, you plug them directly back into the design matrix so that your design matrix expands automatically. So there is a way to do that as well. Okay, so ignore these warnings. It's basically complaining that we created the XML metadata on the local machine, but as I showed you earlier, it actually exists on the server as well. So let's look at those logs. So, group 1 didn't match anyone. That's strange.
Because you put a space in between group and one.
Yeah. Right, but there is a space here as well.
But the module name doesn't seem to have a space.
Did I do this thing wrong again? Okay, hold on. See, they're all false, and see, 0 were selected as part of group 1. Okay, so we have to reset that again. So let me see, what did I do wrong now? Let's just double check the group IDs. It's just group 1. There's a space in between.
On the document, the name of the module doesn't have a space.
Here?
Yeah.
Oh no, no.
The label on
Here?
no, this group 1 and 2.
Yeah.
There isn't a space.
Oh, because this is the name of the fork. The name of the fork, I can name it anything I want. It should be just an if else statement. The question is, subject belongs to group 1. Okay, let me try something else. From here I can actually export the groups. Oh my gosh, okay, maybe that's why I export group as an output parameter. Okay, maybe that was the problem. Let's try to check that. Still validating. Okay. All right, so I may have to look at this during the lunch break a little bit. I can't quite get the groupings to reflect properly. So what I'm going to do instead is I'm just going to start the default workflow so that at least I can show you what the results look at the end, and then we'll try to figure out why was this not working well with our own data. So these are the 10 subjects, and how many groups are here? 2 groups. They represent, okay, so they're called group 1 and group 2. So let's try this workflow instead. So I'm going to run this one first, and then maybe during lunch I'm going to have a look at this and try to figure out what's going on. Okay, let's clean a little bit. We talked about that. I can cancel that. Okay, so it's still gonna, see, the workflow is still gonna run. The problem is that all the data is gonna go as one group, and at the end, when I'm beginning to do the group-based analysis right up here, compare group 2 to group 1, it's just gonna break because I don't have the groups divided properly. Okay, anyways, so we'll have a look at this as it finishes. Look what happens in this case. They correctly split into 4 and 6, and that kind of gives it a nice breakdown. Okay, so let's press on, and so we're going to come back to this a little bit later. Hopefully it's going to finish in several hours. Here again is the link to the GSA documentation. Let's look at another workflow, this minimum deformation template. If you ever wonder how people do tensor-based morphometry, have people heard about tensor-based morphometry? So the basic idea is that sometimes when you register data sets to each other to be able to do statistics, the actual information content that the data carries gets pulled into the displacement vector field, and what you get at the end is essentially a skeleton that does not have value. Think about registering 2 hands. Once the 2 hands are in perfect registration, they're quote-unquote identical. There is no differences between them. The differences were left into the displacement vector field. So with this realization, once non-linear, very high order registration came to be, people realized that if you use very localized registration, you're essentially making the data so similar that there's no point of considering the differences into that common space. So then they focused on the actual displacement vector fields. So what is the magnitude of the displacement vector field at every location? What's the direction of the displacement vector field at every location? That's what tensor-based morphometry is all about, and it's called tensor-based because at every location, every voxel, at every location in space, you essentially compute the vector field and you code it as a tensor, where the tensor has a geometric representation as an ellipsoid, where the main direction of the ellipsoid, which has 3 directions, right? The primary, secondary, and tertiary. They kind of tell you, in a probabilistic sense, which way is this voxel traveling to get to its homologous counterpart in the atlas. Is that right here with me? So the question is, how is this thing done? How are these things computed? And how do we actually use that information for subsequent analysis? Well, that's what this 2 of these things deal with. One is called the minimum distance template atlasing, and the other one is the tensor-based morphometry. So in the minimum distance template atlasing, it's a very elegant way of registering a whole bunch of subjects into a common space without using a predefined atlas. The idea is very interesting, okay? You want to construct a hyper-atlas space for your specific cohort in such a way that the atlas represents a phantom that doesn't exist in reality, but this phantom represents the minimum distortion that needs to be done collectively on the entire cohort to bring them into a common space, whatever this common space is. Well, the solution to this problem, if it exists, is called the minimum displacement atlas, or the minimum deformation atlas. And again, it is very specific to the study, okay? But it guarantees the least manipulation of the data, and then obviously all the results are imported on top of this pseudo-atlas, right? You can render a real volume out of it, but it's actually not any specific space. So this has been, implemented very heavily, and then once you have that, there is step 1, step 2, and step 3 in a tensor-based morphometry. The basic idea is that, so the minimum distance template, again, you can keyword search here, and it's got several alternative solutions. So here is one of them. Okay. So you provide the subjects as IMG or NIFTY or something. So in this specific case, you have what's called a directory input source. And directory input means that the pipeline is going to go in this folder and literally extract every file that matches the file types that you toggled on. This could be a mix of Mink, Analyze, Nifty, whatever. It's going to pull all these files and it's going to think of them as the input. So we have to be very careful because if the same directory has additional files that you did not want to include in the study, they will be included if you use that directory input. And then what it does is, a little bit of pre-processing, biofield correction, histogram equalization. The histogram equalization essentially makes sure that the intensity spectra of all images are roughly speaking aligned. The histograms of the intensities are going to be fairly well registered, not spatial registration. The intensity histograms are going to be registered. That's what histogram equalization does. And the first thing that you do is you kind of generate a temporary 9-parameter rescaling spatial normalization of all the data into an atlas space, okay? And then you apply this, what's called the Kublak-Leibniz mutual information registration in multiple steps. So you register, you deform, you register and deform several times all the data, and then you interpolate the average, and then you repeat this process a few times, and what comes out at the end is a deformed template image, which represents your atlas. And then at the very end, what you do is you compute the Jacobian. The Jacobian of a three-dimensional vector transformation gives you just the magnitude of this maximum tensor direction. So if you think about the Jacobian being represented as these ellipsoids at every voxel location, just the magnitude of the major direction of the ellipsoid variability, the Jacobian kind of returns that extreme. And now this can become itself, you can think of it as a functional measure, structural measure, some kind of an additional imaging biometric which you have at every location. Which, by the way, typically gets correlated. So you see, instead of looking at, if you're doing some kind of an imaging association study, instead of looking at the intensity, the color of the tissue maps at every location and correlating this across groups or across phenotypes, what you're going to do is you're going to take the magnitude of the displacement vector field, and if some individual is closer to this MD, minimum distance template atlas, their corresponding Jacobian is going to be smaller, and if somebody is farther apart, the Jacobian is going to be larger, which indicates a lot of displacement had to happen for this individual there. So your response, your imaging response is not the scanner provided color for the corresponding water hydrogen amount, I guess, at this location, but rather how much displacement you have to do. So then you save those Jacobians for later analysis, and then ultimately, as shown up here, you go through these steps, reconciling, pulling the non-linear things together, and finally this third step, I believe. Oops. Okay, so this link may be broken a little bit, so let's see.
So the Jacobian is kind of like the average of all of the subjects. It's kind of
No, the Jacobian is just for one subject. Every subject has a Jacobian map. It essentially tells you, maybe I can draw you a diagram here. In 2D, if you have your subjects, for, and your MDT atlas is here, and you morph all of these guys. Okay, so this could, yeah, so this could, you're absolutely right. I don't think I've ever done it this way, but this could be the same subject at 3 different time points indeed. Most of the time we do it with multiple subjects cross-sectionally, but I suppose if you're interested in tracking the atrophy or some kind of a longitudinal change of the brain of one individual, you can do this within subject as well, without doubt, yeah. So, and the displacement vector field, remember, this thing is essentially something that looks like this. At every location in space, outside of the brain, it's going to do nothing, right? But inside of the brain, these are going to be some small vectors, you know, that kind of move about. That's the transformation phi 1, and then the Jacobian of phi 1 is going to be just simply on yeah. So what I typically do is I look at the the FDR corrected p-values. Let me see there here. Okay, let's look at the, okay, so I look at the FDR corrected p-values. It's always best when the thumbnail works because you don't have to download all the 40 megabytes. It just takes a cross-section, very minuscule rasterized volume, and that's what it shows you. Not sure why this is let's try this. Let's hope the thumbnail shows up. I typically look at the FDR corrected p-values, and if I have any, you're not guaranteed to have any, but if you have any hot spots, these are the regions where you want to look at, let's say, the beta, because you're ultimately interested in the effect size. But the question is the effect size significant? And that's answered by the p-value. The problem is that the p-value is uncorrected for the millions of tests that happen here. So that's why, right, I have 181 by 217 by 181. There's millions of tests that are done, right? And that's exactly why you have the option of providing a mask to narrow down the region that you're interested in, so that you minimize the number of statistical tests and maximize your power to detect an effect, right? So, but ultimately you want to know, well, how is this specific regressor predicting my Jacobian change, or even my PET intensity at certain location, you know, whatever the outcome imaging characteristic is. Is this making sense?
So you're saying that you want to look at the FDR,
Yeah.
that is going to tell you where the false discovery rate is the maximum?
No, the FDR is going to tell you if any of the p-values that you have in this volume, because this is a solid volume, it will have bright regions and dark regions, just like you have up here. Okay, you see, the bright regions are the areas where the probability is close to 1. In this specific spatial location, I don't have a high association between the grouping and the Jacobians. But in the regions that are darker, like up here, or grayer, there is some evidence that there may be an association. The question is this evidence strong enough? And the answer to that question is included in the FDR corrected p-values. So what FDR does in this case is the following, right? Suppose the p-values look like this. The distribution of the p-values, you know, 0 to, let's say, 1. So the distribution of the p-values may look like, I don't know, something like this. There's lots of ones, and it's hard to exactly depict what's happening here. But if 0.05 is here, lots of these p-values are going to be, so remember, they're kind of dispersed across the entire grid, right? They're dispersed across the entire grid. Some are close to 1, and you don't worry about these, and some are close to 0. I don't know how to denote these because they're not really zeros. They're 10 to the minus third, 10 to the minus fourth, 10 to the minus fifth. You know, some kind of a, let's call approximately 0. Okay, and what the FDR does is it's going to take these p-values and it's going to make them, you know, it's going to leave the ones that are very significant here, but then it's going to make everybody else a 1, right? So the question is, what is this, you know, what is that point of threshold beyond which it's considered to be significant? And, you know, because you never know, right? I mean, you know, is this corresponding to something significant? Well, it depends how many tests you run. Roughly speaking, the more tests you run, the lower, the more p-values you're going to be thresholding, essentially making them a 1, insignificant, the more tests you do. And again, if you have a smaller region of interest, that's more likely to yield something that's beyond reasonable doubt, if I may say so. So anyways, here you're going to be interested in those black regions because they're the ones most likely where something happens, but because these are uncorrected, you don't really know if that's the case. And unfortunately, the thumbnail here for the FDR is not working. I did start the download. Okay, so wait a minute. So I think. Oh, but you know what? Okay, so you have to be careful here. Only the IMG volume is downloaded. It does not have a header, which makes it not an official analyzed imaging file. So this still can be opened with image J by specifying, remember these dimensions you guys here, and the corresponding these dimensions, and the corresponding step sizes. So image J allows you to open raw files, raw byte files, if you tell it how to cut them into rows, columns, and planes, and if you tell it how far apart are each voxel, just like we have in this case isotropic, so you'll be able to consume it and load it. Now, Eric may not have here on his machine image J, but I can help you install image J. We can look at some of these files. They look exactly like this small thumbnail image that I'm showing you now, except that the FDR corrected is going to have a lot more white, and maybe just some sparse black, indicating that these are the locations where the statistical significance is beyond chance. Okay? So, again, I don't know exactly, because maybe the p-value did not have a header file. That's right, okay. The p-value did not have a header file, and maybe that's the FDR does not have a header file to push downstream to show what it looks like. Okay, anyways, so these are statistical issues that we can go deeper into this. All right, so what remains to be done is to have a look at how we integrate R, some of the R routines within the pipeline. We are going to do this after lunch, but I want to hear now what questions or what, I don't know, specific examples you guys want to look at. For instance, FMR, diffusion weighted, or anything else that anybody wants to look at. We might be able to run some of these examples that are included here. Does anybody have anything in mind? Or, you know, I can certainly start a lot more of the other ones, and as they begin to finish, we can look at some of the results. Again, most of these do take, as you can see here, this one is some time into it, and it's still number crunching. Yeah, see, my client is not very responsive, so I'm going to have to close the client, reopen it. That's not going to affect the running status of my workflows. But you see, because I'm not getting a response from the graphical widgets, I'm beginning to be a bit concerned here. So why don't I close this and reopen it? Okay, let's save that. Okay, should we save this one? This is the MDT, okay. This was the global shape analysis. Oh, there's another one that's very interesting called local shape analysis. If you suppose you're kind of focused only on one region, hippocampus, caudate, it doesn't matter which region, and you will know if there are vertices on the surface of the hippocampus. So remember how the hippocampus have different nuclei, right? And the thalamus, they're subdivided into nuclei, okay? You want to know, is the head or the tail of the caudate more impacted by dementia or trauma or something like this? So there is a local shape analysis workflow in the pipeline that allows you to do exactly the same analytics, but per vertex on the manifold. In other words, you model the shape of the boundary of the region of interest, and now instead of voxel locations that allow you to traverse through space, you traverse the manifold by vertices on this triangulated representation. Now, you can do exactly the same statistical tests of association of clinical and phenotypic features and the corresponding imaging biomarkers, like, for example, the displacement of every vertex in certain direction as you register these shapes, or perhaps the imaging intensity underneath that voxel that corresponds to the place where the boundary intersects the anatomy. So you can do some of these things as well. They're very effective. It essentially generates at the end color-coded shape models where the colors represent exactly the same metrics, either effect sizes, t-statistics, correlations, or probability values, right? So you can imagine how you can generate these color-coded surface models with hot colors corresponding to significant change and cooler colors corresponding to insignificant changes. Let me see if I can. Now these are pretty fast because the regions are small. So here's the local shape analysis with study module perhaps. And then we're going to have a look at how many of these sessions might be completed. Oh yeah, okay, so just to orient you a little bit about what's happening here, and maybe I'm going to start this, but I want to see the other one as well. So basically what's happening here is you do exactly the same brain parcellation to find the corresponding masks of the 56 regions of interest. Then what you're going to do is you're going to construct mesh. You're going to estimate the boundaries of these regions, and then you're going to register these things to a sphere. Okay? Each of these regions is, because the sphere represents a canonical space, just like you have brain atlases for structural brain data, you have canonical spaces for shape data, and these canonical spaces are typically spheroidal. So you co-register to a sphere, and then you compute radial distances. These are the, just like in the tensor-based morphometry, where you look at the volumetric change. Here you look at the shape registration and how much is the shape being morphed locally at every vertex. These voxel locations in the structural brain images are referred to as vertices in the shape space. And then you compute these radial distance measures, and then you compute Gaussian. You smooth them up a little bit because they can be a little bit too jagged. And then once you smooth them, you essentially compute a permutation test, a non-parametric equivalent to the t-statistic, to find out what's associated with these things, and then you color code these p-values. And finally, you have these p-maps that are again color-coded surfaces representing a specific association. Now, this will be another couple of hours of work. Let me just see. All right, so I'm going to start that workflow as well. Hopefully it will finish within a couple of hours. So we can look at some of these results. So again, just to recap, we saw some structural volumetric statistics using the volume linear modeling routine. The input volumes could be either the raw MRs or function, they could be functional data as well, or in the case that I showed, actually there were Jacobian matrices derived from the structural data. You can do, in addition to the volume-based analysis and tensor-based analysis, you can do shape morphometry analysis by doing exactly the same statistics, or maybe different statistics, including non-parametric permutation tests, but on the shape spaces. And there are examples as well with, right up here, with functional magnetic resonance for FMR. These are very basic ones, so you will need to modify these if you're interested in. Right up here, there is a basic fMRI pre-processing workflow that you can do. And there is a whole bunch of diffusion tensor imaging and DSI workflows that we can go over as well. So are there anything specific that resonates with you guys? I'm trying, it's a bit difficult to gauge where your interest might be. Or if there's no specific interest, that's fine as well. We just need to wait for these guys to finish, and then we're going to go over the interpretation. Some of the visualization, again, if you intend to use three-dimensional and four-dimensional volumes, you have to download ImageJ, download MePath, download Brain Suite perhaps, and that will probably get you most of the way there in terms of visualization. Sometimes MePath is very nice because it allows you to superimpose two brain scans, and especially in the situation where you're not sure the orientations of two scans are proper, that is identical, when you overlay them, they're either going to show in the right orientation or not. So that's when you know that you need to flip or reorient or mirror image, or some kind of an operation that only a human can do, because for machine it's very difficult to identify when two things are not properly positioned, I guess, in space.
What is the activation you mentioned?
So let me just show you. So one would be MePath. medical image processing, analysis, and visualization. It is a very nice tool. I use it all the time. You can download this. The other one is called ImageJ. Coming again from the National Institutes of Health. They're all free, downloadable for all platforms. I believe they're both Java-based. You have Brain Suite. As well, brainsuite.org. Mine too, I wrote, but it's kind of old now. LONI Viewer is what I wrote, 15 years ago. It was pretty good. It allows you, volume rendering as well as cross-sectional views, overlays and whatnot, but it hasn't been updated for at least 7 years, so it's not necessarily going to consume 50 files or something like that. So it's, for if you're going to be dealing with shapes, if anybody will be analyzing shape morphometry, you probably need to get something like the shape viewer. Right up here, LONI Shape Viewer. It has some really cool graphics. All the LSA results are visualized in the Shape Viewer. Yeah, these screenshots don't do justice here. Let me show you what's slightly better. So whenever this, remember I started this, whenever it finishes, it would generate, unfortunately there isn't an example here, but if you want I can show you later on my machine. It essentially generates color-coded surfaces, again, illustrating where is the significance, where is the impact, where is the association that you're going over with, that you're examining in 3 dimensions. So, that's the fMRI. Okay, we looked at this. This is working. If anybody is using SPM for, I don't know, either fMRI or PET statistics, there are SPM modules here. SPM 8. Because SPM is MATLAB based, you can actually look at these implementations if you have your own MATLAB code and see exactly. We actually wrapped it up, that's right. We wrapped it up in shell scripts because untangling the MATLAB source for SPM and splitting it into individual SPM MATLAB executables and transferring outputs of one into inputs into the other one was a bit challenging, so that's why we wrapped them into shell scripts. But you can look at some of these, and we have a lot of things. FreeSurfer. If anybody's interested in doing recon all, tissue classification, parcellation, an alternative way of parcellation, modeling the cortical surface really well, parcellating the cortical surface itself, and reporting some measures like volumes and surface areas and whatnot.
So this has interface with SPA,
Yeah,
not the
12. With 12, no, we haven't wrapped 12 yet. Depending upon how much how much has changed, the same scripts can be used to expand that. But you know, it's not. To be honest with you, getting this to 12, version 12 is not a top priority, and I'm not sure when it's going to happen. So, if anybody's interested, that you may have to do this on your own, or perhaps help out.
So post-lunch, can we even have a demonstration of scripting using R as well as MATLAB?
Yeah. So we're gonna do. Okay. So we're gonna do the R example now. Mostly, I want you to do. I'll show you an example, and I want you to do something to learn, I guess, from the experience. For the MATLAB, here is the pipeline invocation of MATLAB scripts that kind of shows how this is done. There is a PDF documentation and an example pipe workflow. So, all right, so you guys, again, from the home page, from our home page, you just need to go to the to any of these, I guess, any of these that are on the wiki, okay? And then I did a keyword search here, remember, for MATLAB directly on the main site. And you can see the script example. So it is a bit tedious, because you need to use the MEX MATLAB compiler to export a standalone binary, and it needs to be done specifically on the server that the pipeline workflow is going to be calling. Sorry, I don't know why this link is broken. Let me see if I can search. I will find that document for you. It has a 5-step process to encode that. So let's try to maybe start the R invocation. How do you wrap up R? And then we're going to have a little break, and then we're going to do the little example. So the R script is just above from the MATLAB script. So this example, by the way, is right up here. It's under LONI R script example. So let me walk you through how this thing works, and then we'll see the challenge that I'm going to present to you. So roughly speaking, you have 3 inputs. The first one, you don't have to worry about these set of flags. Let the pipeline invoke R in batch headless mode, without a GUI, without a window, without a shell, okay? So you typically don't manipulate these flags unless you want to perhaps request more memory for R or something like this. You can add to that list of default flags when an R virtual machine starts. The second set of parameters includes all the arguments that you want to include, that you want to actually send to the script from the workflow. These could be numbers, these could be strings, these could be file names, whatever you need to do. So I'm just showing you examples. You know, I'm calling the first argument arg1, the second argument arg2, the third argument arg3 equals to 3. The fourth argument is arg4 is equal to a string. The last argument is argument 5 is equal to a file name. These are just placeholders for the actual arguments that you want to plug in. And then, the most important thing is the reference to the R script that you want to actually invoke. Now, your R script must be in perfect agreement with these input arguments that I just provided you, because these arguments are going to be sent to the R script at invocation time, and it needs to be able to handle them gracefully. So this is the now the R script can come from the local machine. It doesn't. In this case, it's on the server, but the R script could come, and I'll show you an example from the local machine. It still will be piped to the server because that's where the R execution is. You don't want the R execution. Well, actually, let me take this back. You can run the R script locally, I suppose, on your machine as well. You don't have to send it to the server, but if there is a lot of calculations in the R script, then it may be justified to send it to the Cranium server and let it number crunch there. And then here is the wrapper. Here is the wrapper of this R script. It essentially calls R, as you can see. It calls the R environment. And I don't know, sometimes this may have to be REXE if it's a local run or something. And it says, where is this thing located? And then it simply defines these parameters. General flags that are operating system related for the batch mode execution of R. The user provided arguments that the R script needs to do its job. Okay? The reference to the R script and the output stream results. Where should the output stream results be redirected? Because the R script may be generating some outputs that need to be saved somehow. Okay? And then, you know, you just save it into, this could be again, it's on the server. I can make this local. Let's make this local. Let's browse this. Browse the local file system and save it locally. And what should we call this? So it has to have a name. Okay, well, let's select something. I'm going to call it test R .txt. Text file, that's fine. And I'm going to run this. Oh, by the way, let me just, before I run this, because this executable, you guys, no, this is an executable that's already predefined. Some people don't know how to write an R script, we do, but this is predefined. So let me just download it at the same time so that you can see what's in it, okay?
So if we write our own script, we can actually run it locally by giving a path from
Yeah.
our system.
Absolutely. So I'm going to demonstrate both of these. So what? Okay. So why don't we? Okay. So what we got? This is a very quick thing. Okay. So I'm going to do a data sync, and I'm going to call it local R, and I am going to put it in the same place. I'm going to So you see, I'm just going to grab, what this thing does is it just grabs from the server the script that's going to feed into the executable, and it's going to save it locally for me, right? So I see, so that I can see what it is and what it does. So let's do a quick validate. Okay, validation passes, so let's go ahead and run this. Again, because we're running so many workflows here, we are making a good use of the server. 64 jobs are running just for me right now. And while this is number crunching, I want to do what he just suggested a second ago. Run everything locally. Not even worry about the server, right? Now, I don't know. Obviously, one thing to keep in mind is that because of the enormous availability of our packages, the Cranium server doesn't have, for example, the MX net library that I showed you for the convolutional neural nets that we did for the imaging. So, maybe it's justified sometimes to run things locally as opposed to sending them to the server. Although the team is pretty good, if we tell them we need this library, they will build it for us. We're going to have it. But remember, I mean, everybody has different needs. There is no way that any server is going to have all the our libraries. Yeah.
So on those lines, is there any support for containerized tool like either Docker or one of the other ones that are security approved?
And that's a good question. Not currently, but it doesn't mean that it cannot be done. So if we can draft, I guess, an example or a set of requirements or something, or a set of steps to build that, I'll bring it up to them, and they most likely would say, yeah, they'll build it.
Something like that, yeah, that issue he was talking about also.
Yeah, absolutely. Okay, so let me see here. Let me copy all of these. Select all, copy, open a new workflow, paste them in. And now the only thing that I want to change is I want to change the location of the R script from the server to the local one that we just downloaded. So this is not going to be on the server anymore. This is going to be local, and I'm going to specify a local host and okay that. So local, local, local. Now I got to change that. So let's see. So I need to say that this is execution on, okay, so how, I need to browse it, wait. Not remote, that's going to be local. And R, well, let's find out. R should be under applications. R. Wait, is it here? Yeah. Okay. Does everybody see what I'm doing? I'm just changing the reference to R from the reference to R on the remote Cranium server to the reference to R on this specific machine, because I want to run a local execution of the very same thing. So I need to be getting the same results at the end. Okay, that. So local, 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 let's just validate that. Oops. I meant validate. Oh, because this, okay, remember I started copying, but the copying, for some reason, is not finished yet. Oh, this was, okay, that's fine. Why is it waiting for so long? I may have to restart this one. I don't understand why it's waiting for so long. Run. It's entirely possible because I've got so much going on. My jobs might be queued until some of the other things complete. Even though I'm within my quota, I think there is a cap on how many. Oh, there may be a cap on how many sessions. I thought you may be having only 10 sessions or so. Let me see if I can kill some of these sessions that we are kind of done with. This is the brain suite. We've looked at this thing. I'm going to wipe that out to release a little bit of resources. Get rid of this. Okay, so what's happening now? Okay, this we know because that was a local version. I haven't finished downloading that yet. The local shape analysis, that's running. We're going to leave this to run. What else do we have? Volume regression analysis, I think we're done with that. Unless somebody wants to see, does anybody want to see some of the data? I may have to install some of the tools here because we don't have them. But this is easy to recompute. I can always recompute it. Okay, so I'm within 10 now. Yeah, we're done with this as well. I'm pretty sure, so I can reset this workflow. Okay, so let's do now the interesting things. Sorry, I need to restart that. Not sure why it doesn't want to. So some of these problems that I'm encountering might be related to the fact that I'm using, I'm a guest, no authentication here. There may be some limits that I don't know about, but we're probably gonna resolve these. Okay, so this is still not working. Strange. Okay, I'm going to remove my edit and see if the default one works. I know it does because it did work this morning. I'm surprised. Okay, that's cute, complete. Let me see. Execution info. Okay, so let me just walk you through this, and then I'll try to pull out exactly from the server this R script, which I promise I'll do. So look what's happening here. So this only took 160 milliseconds to send this R script, well, to actually run this R script with the arguments that was provided. And then the results, you guys, this is the command line that got ran actually. Cos R, all the headless parameters. Then it sends the minus args. These are the arguments that we provided. And then redirects this pipe symbol, redirects the R script into it. This is the R script, and outputs all the standard output into this temporary text file. So on the output stream, there is nothing, because the output stream was captured by R. In the error stream, there is nothing, and here is the output stream. So I can view this, and it simply says, okay, it says reading arguments. That's, by the way, reported directly from the R script. So we did call R, and it simply reports for us. The arguments are input, all the slaves, the arguments, simply reports the arguments back as output. So let's go ahead now and try to see why did it complain about including, I should want to continue, yeah? Why did it complain about including another data sync here? Okay, this is local. Yeah, let's just use a directory dump then, see if that's any better. Let's use that. Okay, so wait a minute. Choose. Okay. So suppose I want to dump this here and run that. Remember, I'm trying to pull back from the server this R script so that I can do the local execution. Staging, that's a good sign. But for some reason it doesn't finish. Let's have a look. Is there a way to arrange them by date created? Somebody with a PC, were you guys able to download this R script? Because I know I tried this morning, it was working. I wonder if it's a Mac issue. See this staging, it tries to download it and it never finishes it. So my computer is a PC and it did work in the morning, so I wonder if there's any Mac issue here. Can somebody confirm if you guys can just put in a data sync to this R script, which is right up here under the LONI workflows. Under the workflows, LONI, and then the R script that's a little bit towards the bottom. If you add up a new data sync and save that R script, does it complete? Another thing that I can try to do, you see, is try to include that R script right down here and edit this module maybe. Parameters, maybe I can add an output file, R script. R script, and let me see, dependencies. It depends on the executable R script. Transformations, no transformations. Okay. Let me see if that'll work. Ah, okay, so it did download it. That's strange. Oh, okay, finally complete. Okay, so what I did, you guys, is I twisted it a little bit. Remember, our test script.r is the name of the file. And then I downloaded here by, instead of going directly from here to over here, I said, well, let's define a new output parameter that has this dependence upon this input. So the input is actually fed in as an output. And this took a while, but it did copy the script locally. And that's what the script looks like. Oops. Where did it go? No. Right up here is the script. I can't zoom that. Sorry, I can't zoom that, but it is a very simple R script. Let's look at what it does. First of all, it's got a little documentation here, all these sharps that are ignored by the R interpreter. Then goes beginning of the real script, print the arguments. It cats reading the arguments, okay? And then this is the command. Command args parenthesis in R retrieves a list of arguments. Each of them is a string, and it goes ahead and prints them out. For each argument in the list of arguments, cat space and then the argument, and put a new line. Now just reads the arguments and prints them out. Very simple script. It doesn't do any calculations. But you can imagine how if one of these arguments was a file, I can use the file to read the data. If one of the arguments is some kind of a specification, I can apply the specification, and ultimately you write out a file or something that comes out. And in this case, I just exit with a 0 code saying that, you know, everything is fine.
Can you show again how did we downloaded the script and just arrange?
Yeah,
it?
so what I did, on a PC, I don't have to do these acrobatics. I'm not exactly sure why it's not working here. What I did is the following. So let me just keep this for a second. Okay. So what I did is, let me disconnect this. So what I did is I just modified the definition of this R wrapper. Didn't have to change anything other than added up a new output variable. You see, and it's a file. And here under dependencies, I said that this output variable is going to be exactly the name, the variable that is the input file R executable script. So every output can depend on input. And in fact, I could have changed, if you go to transformations, I can change that name by telling it something else. Now, so what happens now is this output, you see, it's an output because input is not checked in, is going to be exactly the same as this input, right? And again, I'm not exactly sure why in this Mac environment I have to do this. And I simply connected it, and then I ran it, and it saved it out.